Welcome to the debate. So imagine holding a photograph of a speeding train.
Okay.
It's a perfectly clear, high-resolution image captured at just a fraction of a second. You can see the paint on the engine, the exact position of the wheels on the track, the smoke suspended in the air.
Right, a complete freeze frame.
Exactly. But looking at that static image, you cannot measure the concept of travel. Travel requires time, it requires movement from point A to point B.
And in thermodynamics, we actually face a very similar conceptual divide. If you take a snapshot of a thermodynamic system, say a massive boiler operating on a factory floor, you can measure its pressure, its temperature, its intrinsic energy.
The state variables.
Right. But you cannot measure its heat or its work. Those are things the system does, not things the system has.
Which brings us to our topic today. We are exploring the fundamental nature of energy in thermodynamics. Specifically, we're looking at the critical distinction between heat and work as energy transfer processes versus intrinsic system properties like enthalpy.
And this whole discussion actually emerged from a fascinating set of university-level thermodynamics lecture notes and factory boiler engineering worksheets, specifically from Massey University.
Yeah, it's really rich material. I'll be arguing that the theoretical path dependence of heat and work is the indispensable conceptual framework of thermodynamics. It's essentially the invisible rulebook that dictates absolutely all subsequent engineering.
While I'll be representing the perspective that practical process engineering, specifically utilizing factory floor applications to manipulate state variables and determine enthalpy, is the true core of applied thermodynamics.
Bypassing the theory, basically.
Well, the theory just tells us what we can't do. The brilliance of the discipline is how we effectively bypass those theoretical limitations to just keep the factory running.
Let's start by establishing the ground rules for anyone, perhaps a student, who is first wrapping their head around these concepts. To truly understand thermodynamics, you have to grasp a reality that feels, honestly, deeply counterintuitive.
Which is that heat and work are utterly meaningless at a static point in time.
Right. They aren't properties of a system. You can't bottle up a kilogram of steam and say, oh, this jar contains 10 joules of work or 20 joules of heat. It's physically nonsensical.
Because heat and work are verbs, essentially. They are purely amounts of energy transferred across a boundary over time.
Exactly. They exist only in transit. And because they are transfers, they are completely dependent on the specific process path taken between two states.
The classic pathway problem.
Yeah, think about heating a gas. If you lock that gas in a rigid steel tank and add energy, the volume can't change, the boundaries don't move, so zero work is done. All your energy goes straight into raising the temperature.
But if you put that same gas in a cylinder with a movable piston, it's a completely different story.
A fundamentally different physical journey. If you let the gas expand to keep the pressure constant while you heat it, the expanding gas pushes the piston upward. It's doing work against the atmosphere.
Right, it's expending energy to create space.
Exactly. Because some of your input energy is being spent moving that piston, you actually have to pump more heat into the system to reach the same final temperature as the rigid tank.
So the destination is the same, but the trip is totally different.
You started at the same initial state, ended at the same final temperature, but the amount of heat transferred and work done are completely different. This path dependence is the inescapable foundation of the science. If you don't construct your understanding around how energy physically crosses a border, you are just blind to the limits of what a system can do.
See, I come at it from a completely different angle. Everything you just laid out about the physics of path dependence is technically correct, but let me tell you a secret. Plant engineers absolutely loathe path dependence.
I'm sure it's inconvenient.
It's worse than inconvenient, because heat and work depend on the exact process mechanism, like every little friction loss, every minor temperature gradient. They are incredibly difficult to measure reliably in a complex, continuously operating plant.
Sure.
Heat and work right out of our mathematical models.
But you can't just pretend the foundational modes of energy transfer don't exist just because the math is messy.
We don't pretend they don't exist. We rely on state variables, properties that are true in that static photograph you mentioned at the beginning, properties like pressure, temperature, and most importantly, enthalpy.
We should probably define enthalpy clearly here because it's basically the central character of this entire debate. It's not just internal energy.
Right. For anyone trying to conceptualize this, think of a substance's internal energy as the microscopic jiggling of its molecules. But to put that substance into the real world, it has to push the atmosphere out of the way to make room for itself.
The pressure-volume work.
Exactly. Enthalpy is the sum of that internal energy plus the pressure-volume work required to carve out its physical space in the environment. It's the total energetic footprint of the substance.
And it's a state variable.
Which is the beauty of it. It doesn't care how the steam got there. It only cares what state the steam is in right now.
But relying purely on state variables creates immediate line spots. Let's trace the journey of steam in a practical factory scenario. We have a factory boiler turning water into steam, generating a mainline pressure of 30 bar and a temperature of 233.9 degrees Celsius.
Okay. A standard high-pressure main line.
Right. The classic dilemma for any student learning thermodynamics hits right here. Your precious state variables have suddenly failed you.
I wouldn't say they failed. You've just hit a phase transition.
But that's exactly the problem. At 30 bar, water boils at 233.9 degrees. Inside that mainline pipe, you don't have pure gas. You have a chaotic boiling mixture of liquid water and vaporized steam coexisting at the exact same temperature and pressure.
Saturated steam.
Yes, and because they share those exact same state variables, your pressure gauge and your thermometer are entirely useless for telling you the steam quality.
The specific ratio of vapor to liquid?
Right. If you don't know the quality, you don't know the enthalpy. You have no idea how much energy is actually flowing through your plant. Your preferred practical variables leave you completely in the dark at the most critical point of the process.
Well, they leave you in the dark only if you stop engineering. This is where practical application outshines theoretical hand-wringing. Because we can't measure the quality in that boiling mainline easily, we use a brilliant mechanical workaround called a throttling calorimeter.
Which I would argue relies heavily on theoretical manipulation.
Let me explain what it does physically first. We divert a tiny sample of that unmeasurable 30-bar steam from the main pipe and force it through a tiny restriction, a throttling orifice.
Okay.
We exhaust that throttled steam into a separate chamber where we measure it again. Through that restriction, the pressure violently drops down to 100 kilopascals, and we get a new temperature reading of 125 degrees Celsius.
But wait, why does dropping the pressure solve your measurement problem? You still have steam, it's just at a lower pressure now.
Not exactly. And this is the magic of the device. Think of it like trying to weigh a wild animal. You can't get a good reading while it's thrashing around in the wild.
The boiling, saturated steam mixture.
Right. So you open a small door and let it run into a controlled cage where it calms down. By dropping the pressure to 100 kilopascals, we fundamentally change the environment. At that low pressure, water boils at just under 100 degrees Celsius.
Ah, but your thermometer reads 125 degrees.
Exactly. We have forced the steam sample completely out of the saturated boiling region and into a superheated state. All those liquid droplets have flashed into vapor. Once it's superheated, pressure and temperature become independent again.
So you can just use the tables.
We just look at our superheated steam tables, match the pressure and temperature, and read the enthalpy directly. It's 2727 kilojoules per kilogram.
I mean, it's clever, but I don't buy the framing that this is a victory of practical workarounds over theory. In reality, the throttling calorimeter is a thermodynamic trick that weaponizes a deep theoretical understanding of energy boundaries.
How so?
Well, why does knowing the enthalpy of the superheated exhaust tell us anything about the boiling mixture back in the high-pressure mainline?
Because a throttling process is enthalpic.
Exactly. It's a constant enthalpy expansion. The valve happens so fast and is so well insulated that there's no time for heat transfer. And because there are no moving parts like a turbine blade, zero work is done.
Right.
Therefore, the theory dictates that the enthalpy of the steam entering the valve perfectly equals the enthalpy of the steam exiting the valve. You aren't avoiding path dependence. You are relying on a highly specific, carefully controlled theoretical path, an adiabatic zero-work expansion, to reveal the original mainline's enthalpy. The theory is doing the heavy lifting here. The hardware is just the messenger.
That's a fair point regarding the physics, but the theory is only useful because it results in a functional piece of hardware on the factory floor. The theoretical understanding of an isenthalpic process is great on a chalkboard, but the physical sampling tube and the thermometer pocket are what actually allow the plant operator to verify the steam quality and keep the factory safe.
Let's follow that steam journey further down the line then, because measuring energy is one thing, but actively controlling it is where the physics gets truly demanding.
I completely agree. Let's pivot to control. So we have a different scenario now. Our boiler is producing superheated steam at 6 bar and 200 degrees Celsius.
Okay.
However, the factory machinery downstream, maybe it's a massive heating jacket for a chemical reactor, actually requires dry, saturated steam at 6 bar. It doesn't want the extra sensible heat. It wants steam right on the delicate edge of condensation to maximize heat transfer efficiency.
So you have to reduce the superheat.
We have to get rid of it, yes.
From a fundamental first law perspective, you need to reduce the specific enthalpy of the system. To lower the energy content of that steam, you must transfer energy across the boundary. You could extract heat by running the steam through a heat exchanger, passing that energy to a cooler fluid. Or you could extract work by running it through a small turbine to drop its internal energy. Both are standard theoretical pathways to alter the state.
Well, a plant manager would laugh you right out of the building if you suggested putting a heat exchanger or a turbine in the middle of a steam line just to drop the temperature.
Just because of the mechanical complexity?
Because it's incredibly expensive, introduces massive pressure drops, and requires heavy maintenance. In industrial steam systems, engineers don't try to extract heat or work across a boundary to solve this. They use a de-superheater instead. We completely sidestep the headache of path-dependent heat transfer out of the pipe.
By manipulating the mass balance directly?
Precisely. A de-superheater is essentially a highly engineered mixing valve. We take our superheated steam and we literally spray a precisely calculated mist of cooler liquid water directly into the steam flow.
Ah.
The superheated steam flash boils that mist. It gives up its own excess energy to vaporize the water droplets. We don't remove energy from the pipe, we just dilute it. We redistribute the existing energy among a larger number of water molecules until the entire combined mixture arrives at that perfect dry, saturated state.
I have to admit, the mechanism is undeniably elegant. Instead of agonizing over surface areas and heat transfer coefficients in a massive heat exchanger, you're using a thermodynamic loophole. You alter the specific enthalpy, the energy per kilogram, simply by adding more kilograms of a lower energy substance.
And we solve it using a steady-state mass and energy balance. We assume steady state, we assume the pipe is insulated so heat transfer is zero, and there's no work being done. It just strips away all the calculus of path dependence.
It simplifies the math.
Massively. We have two streams coming in, the superheated steam and the liquid water. We have one stream going out, the dry saturated steam. The equation simplifies beautifully to an energy balancing act. The energy entering must equal the energy leaving.
Which means you just apply the specific enthalpies to the mass flow rates. The mass of the hot steam times its high enthalpy plus the mass of the cold water times its low enthalpy must equal the total combined mass times your target enthalpy.
That's it. It's straight algebra. You look up your state variables in the steam tables, you find the enthalpy for the superheated steam, the enthalpy for your liquid cooling water, and the enthalpy for your target saturated steam.
And just solve for the mass ratio.
You run the numbers to find the exact ratio needed to balance the equation. In a typical scenario, it might work out that for every 1 kilogram of superheated steam, you only need to inject a tiny amount, say 37 grams, of liquid water to hit perfect dry saturation. No complex integrals required.
I see the appeal. It perfectly demonstrates how enthalpy is tied to the mass of the system. But notice the massive caveat you brushed past to make that math work. You said, we assume steady state.
Well, it's a highly reliable assumption for a continuously operating plant.
But it's not the complete reality of the physics. Your ability to rely on state variables and simple addition depends entirely on the system being stable over time. What happens when that boiler first fires up? or when a massive piece of machinery downstream suddenly goes offline.
You get transient energy fluctuations.
You get chaos. During startup and shutdown, the change in energy over time is definitely not zero. The massive steel pipes are cold. They are actively draining heat from your steam. Work is being done to overcome initial mechanical frictions.
Sure, things are changing.
The boundaries are actively leaking energy. In those transient moments, path dependence reigns supreme. The engineer who only knows how to read an enthalpy table and assume steady state will be completely lost when the physical assumptions of their simplified equations are suddenly violated.
I don't disagree that startup is chaotic, but factories are designed to operate at steady state for months, sometimes years, at a time. The transient phases are a tiny fraction of the operational lifespan. To suggest that path dependence is the core framework of the discipline is to optimize your understanding for the exception rather than the rule. Enthalpy is the rule. State variables are the daily vocabulary of the plant floor.
Yet, as we established with the throttling calorimeter, you can't even determine those state variables without utilizing a path-dependent trick. You needed the theory of an isenthalpic expansion just to read the temperature and pressure correctly. The theoretical constraints and the practical applications are inextricably linked.
They are inextricably linked, but I would argue the entire history of thermodynamics is weighted heavily toward the practical. The sheer difficulty of calculating path-dependent energy transfers is exactly what drove the reliance on state variables. It was an evolutionary pressure on engineers.
That's an interesting way to put it.
Because heat and work are so frustratingly tied to the path, we spent over a century developing bypass mechanisms like the de-superheater. We didn't solve path dependence, we actively engineered around it to make the math useful.
Convergent. We both acknowledge that the inherent difficulty of measuring heat and work as transient transfer processes is the central hurdle of the discipline. Where we continue to diverge is on what constitutes the true heart of thermodynamics.
Right.
I maintain that understanding why heat and work are non-properties, why they are deeply path-dependent verbs rather than possessible nouns, is essential for knowing the physical limits of our universe. You have to know the boundaries of energy transfer before you can play the game.
And I maintain that the mechanical workarounds are the true genius of the field. Using a throttling calorimeter to calm down saturated steam and uncover hidden enthalpies, or using a de-superheater mass balance to control thermal energy without a massive heat exchanger. That's where the science becomes real. The game is only won when the steam is actually delivered to the machinery at the exact right specification to do the work.
This tension between theoretical constraints and practical process engineering is what makes thermodynamics such an endlessly rich subject to study. And there is far more to explore in this field, particularly when these principles are scaled up to complex power plant cycles.
Oh, absolutely.
We haven't even touched upon how these steam flows interact with the massive turbines that generate shaft work, or the condensers that interface with environmental coolants.
Yeah, when you get to a condenser, the heat transferred out of the low-pressure steam has to be meticulously balanced against the work generated by the turbine upstream. It's a massive plant-wide application of the exact same energy balancing principles we just discussed regarding the de-superheater.
Indeed. We will leave it to our listeners to form their own conclusions on whether the abstract theory of energy pathways or the practical mechanics of state variables hold the true heart of the discipline. But as you reflect on this, I invite you to circle back to that speeding train we discussed at the start.
The snapshot.
Yes. The next time you look at a massive industrial factory, or even just a boiling kettle in your kitchen, remember that a snapshot of its temperature only tells you its current state. The real story, the heat, the work, the sheer power of thermodynamics, is written entirely in the journey.
Thank you for joining us.